For a long time, scientists believed the earliest stages of the universe would remain beyond direct reach. The first stars, the first dense stellar groupings, and the earliest phases of galaxy formation seemed locked behind immense distances and billions of years of cosmic history. Even the most advanced telescopes could only offer indirect clues, forcing astronomers to piece together the past from what survived into the present. That situation began to change with the launch of the James Webb Space Telescope. Instead of just looking farther, it revealed the distant universe with a clarity that had not been possible before. Faint light, stretched by cosmic expansion into the infrared, suddenly became visible in detail, allowing scientists to observe ancient structures more directly. In one remarkable observation, astronomers identified extremely distant and compact stellar systems surrounding a distorted galaxy often referred to as the spark galaxy. These were not unclear or uncertain detections. They appeared as bright, dense systems containing millions of stars, located roughly 9 billion light-years away. Because light takes time to travel, these systems are being seen as they existed billions of years in the past, offering a direct glimpse into an earlier stage of cosmic evolution. Among these structures were objects that strongly resemble globular clusters. These are tightly bound groups of stars held together by gravity, typically containing hundreds of thousands to millions of stars. In nearby galaxies, globular clusters are considered some of the oldest surviving structures. What makes this observation so important is that these clusters are not just old, they are being seen at a time when the universe itself was still relatively young. This changes how scientists study the formation of stars and galaxies. Instead of relying only on models and simulations, astronomers can now observe early stellar systems closer to the time they formed. These clusters act like preserved records, containing information about how quickly stars formed and how early galaxies built their structure. The galaxy at the center of this observation appears stretched and irregular, suggesting strong gravitational interactions. Around it, several bright compact sources were detected. Careful analysis showed that multiple of these are physically connected to the galaxy and are likely globular clusters. Their brightness and mass indicate that they were already well-developed systems at a time when galaxies were still assembling. This creates an interesting challenge for older ideas about galaxy formation. It was once thought that such tightly bound stellar systems either formed in isolation very early or developed later under more stable conditions. These observations suggest a more complex picture, where massive star clusters formed early within galaxies that were still evolving dynamically. One key factor that made this discovery possible is the telescope's sensitivity to infrared light. As the universe expands, light from distant objects is stretched to longer wavelengths, making it difficult to detect with earlier instruments. By capturing this redshifted light, astronomers can study objects not just as they are now, but as they were billions of years ago. Another crucial element is the effect of gravitational lensing, predicted by general relativity. Massive objects like galaxy clusters can bend and magnify the light of more distant galaxies behind them. In this case, a foreground cluster acts like a natural lens, amplifying the spark galaxy and its surrounding structures. Without this effect, these distant systems would likely be too faint to observe. Gravitational lensing can also create multiple images of the same object, appearing at different positions in the sky. This is not an error but a direct result of how space-time is warped by gravity. These repeated images help confirm that the observed clusters are real and physically connected to the galaxy. As scientists refine their models of the lensing effect, they can better estimate the true brightness, distance, and mass of these clusters. This allows for more accurate insights into how quickly such systems formed and how early galaxies developed their stellar populations. The broader significance of this discovery lies in what it reveals about cosmic history. It suggests that large, organized stellar systems may have formed earlier and more rapidly than previously thought. Instead of a slow and gradual process, the early universe may have been capable of building complex structures in a relatively short time. This also reshapes the timeline of galaxy evolution. If such massive clusters already existed billions of years ago, then the processes responsible for their formation must have begun even earlier. It points to a universe that became structured faster and more efficiently than expected. More importantly, observations like this represent a shift in astronomy itself. The early universe is no longer something that can only be imagined through theory. It is becoming something that can be directly observed and studied. These distant systems are not just signals or patterns, they are real structures that have survived across cosmic time. As more observations are made, especially using gravitational lensing, astronomers expect to uncover additional examples of ancient stellar systems. Each new discovery will add detail to our understanding of how the first stars and galaxies formed. What is emerging is a new way of studying the universe, one where its earliest chapters are not completely hidden. Instead, they are still present, carried across billions of years in the light that is only now reaching us. But the deeper astronomers look, the stranger the picture becomes. What initially appeared to be a distant galaxy surrounded by ancient star clusters is starting to raise more complex questions. The structures around the spark galaxy are not just old, they seem unusually bright and massive for their time. In a universe that was still forming its first large systems, such dense and mature stellar groupings should have been far less common. This suggests something unexpected. Either these clusters formed far more efficiently than current models predict, or the conditions of the early universe allowed matter to organize itself much faster than previously understood. Using the James Webb Space Telescope, scientists have been able to analyze the light from these systems in greater detail. By breaking that light into its components, they can estimate how many stars are present, how massive the clusters are, and even what elements they contain. Early results indicate that these clusters may already contain surprisingly enriched material, elements heavier than hydrogen and helium that typically require multiple generations of stars to produce. If that interpretation is correct, it implies that star formation and destruction was already happening rapidly, cycling material through multiple stellar generations in a relatively short cosmic time. In other words, the early universe may not have been as simple or as slow to evolve as once believed. At the same time, the distorted shape of the spark galaxy hints at strong gravitational forces at work. It may be interacting with nearby structures, merging, or being stretched by surrounding mass. This chaotic environment could play a key role in how these clusters formed. Instead of emerging in calm, isolated regions, they may have been born in turbulent conditions where gas was compressed, accelerated, and forced into rapid star formation. Gravitational lensing continues to be a critical tool in understanding this system. As predicted by general relativity, the massive foreground cluster bends and magnifies the light behind it. But this effect is not perfectly smooth. Small variations in mass, dark matter clumps, hidden structures, can subtly distort the images further. By studying these distortions, astronomers are not just learning about the distant galaxy. They are also mapping the invisible distribution of matter in the foreground lens itself. In a sense, they are observing two different layers of the universe at once, one from the deep past, and one closer to the present, both interacting through gravity. And then there is another possibility that cannot be ignored. Some of the compact sources around the galaxy appear almost too concentrated, too luminous, as if they are pushing the limits of what current models allow for globular clusters. This raises the question of whether all of them are truly clusters in the traditional sense, or whether some could represent an entirely different class of early cosmic structure. At this distance, even small uncertainties in measurement can lead to very different interpretations. A slightly higher mass estimate, A different age calculation, or a revised lensing model could completely change how these objects are classified. That is what makes this discovery both powerful and unsettling. It provides answers, but also opens multiple new possibilities at the same time.